In this first part of the review, I'm just going to talk about the material that's going to be covered for test 3. So we started off estimating a parameter, and we did focus on the mean, but technically a lot of these things work for in a similar fashion for any parameter that you want to estimate. But we again did focus on the population mean. So we started off finding the best single number from the sample that best estimates your population parameter, which is called a point estimate. So for the population mean, the point estimate, or the best single number from your sample that estimates the mean, is the is the sample mean. Okay. So this is the point estimate for mu, but again, all parameters have their own point estimate. And the accuracy of this point estimate depends on the sample size, okay? You can see it in the formula. So the bigger the sample, the more accurate your value is. But we also want to get a feel for precision, or in other words, how close is my estimate to that actual population value, okay? So we do that by calculating something called a confidence interval, okay? Formulas, by the way, that are listed here will be given. Okay, so the confidence interval involves taking the point estimate. Notice that this point estimate is at the center of your interval, and adding and subtracting something called the margin of error. That's called the margin of error, which is just using this t-distribution, which means, remember, has degrees of freedom, and multiplying by the standard error. So I do ask you, which one is the margin of error, which is this, and the standard error is this quantity right here. Okay, so make sure you know the difference between the two names. Now, of course, this is the formula I'm going to give you because it's a little more complicated, but all you have to do is, if sigma is known, if the population value is known, then all you're going to do is use z. You should know how to interpret an interval correctly. You know, remember, I'm 90% confident, et cetera, and you should know about the width of the confidence interval. Remember, there are trade-offs in statistics. So for example, if I were to increase the sample size, then we know that that interval is going to get narrower. And we prefer narrower intervals because they give us more information, right? And we know, of course, if we increase our level of confidence, the interval is going to get wider. I highly recommend you go back and look at the videos over these topics so that you can make sure that you understand the concepts, because there will be questions on the exam going over these concepts. So these are the two estimates that we went over. Okay. Now, the next thing we did is given. Oh, and I do want to say one more thing. A confidence interval, remember, after you add and subtract, is going to be in this form. Let's call this lower bound, upper bound. So on an exam, sometimes to make things easier, it might be just to give the lower bound or the upper bound of an interval. So just remember that that might be something that we do instead of asking for the entire interval. And also, I do want to tell you, and I'll repeat this again later, that I will be giving you the formula for the variance so that you can figure out the standard deviation. Okay. Okay. Now, the next thing that we talked about is finding the necessary sample size. So we can take, obviously, we prefer bigger samples because they give better estimates. But what this formula does is it tells you what the minimum value you need given a certain confidence level and margin of error that you're willing to tolerate. So you, as the researcher, pick your confidence level and your margin of error, and this will give you the minimum sample size. Again, sometimes sigma is unknown, and if it's unknown, remember what we do is we take a pilot sample, calculate the standard deviation, and just let that sigma be approximately S. But notice that Z, we always use Z in this formula, okay? Also, once you get this value, remember to round up to the nearest whole number because sample sizes have to be whole numbers, and this is going to be the minimum value. Okay, so that's the minimum value you need, and now we've talked about estimating a parameter up here at the top. The next thing we talked about was not just estimating a value, but making a decision about a parameter. And again, we did focus on the mean. The entire task of a test of hypothesis is really at the end, when you're all done, you're either going to decide to reject or fail to reject H naught. Please understand, the decision we make is always about H naught, okay? Now, we'll go over hypothesis in a minute, but what we do is we calculate our test statistic, and we see if that test statistic falls in the rejection region, okay? Now, if sigma is known, we're not going to call this T star, we're going to call it Z star, right? So I do need to know, since the formula is the same, which one you're doing. So when you're doing work, you should label it as either T star or Z star. So when sigma's known, that the sigma would go here and we'd be using Z instead of T, okay? Now, this comes from the central limit theorem. If sigma's known, we don't have any issues. But if you are doing a t-test, you do have to make an assumption, okay? Remember that we have to assume for a t-test that we have, you remember what it is? We have to assume that we have a normal population. We don't have to assume anything about the sample because we have the sample, we know everything about it. But we're going to assume we have a normal population. But these t-tests are what we call robust. And robust means that you can deviate a little bit from the assumptions and you still get very good results, okay? So we like robust tests, so you can deviate a little bit and the results are still pretty good. Not a lot, but a little bit. Again, when n gets very, very large, you don't have to worry quite as much about this assumption, especially if the data are not heavily skewed, okay? Now, what do we do to set up our hypothesis? We have to make sure that we write down what we're trying to test, and then we make our decision about that, making sure that the equal sign is always in H naught, okay? We make sure that our equal sign is in H naught. What H1 allows us to do is it allows us to tell what kind of test we're doing. So for in this case, this is a one-tailed test and it points you in the correct tail. So this would be a left-tailed test, and we would put all of alpha into that left tail. Okay, so H1 basically tells you what you're doing. So this is a left-tailed test. If it was pointing this way, it would be a right-tailed test. And then here, of course, we would have a two-tailed test, which means we would divide alpha in two. Okay, the next thing, so the traditional method, by the way, of conducting a test is to check whether your test statistic falls in the rejection region. If it falls in there, we would reject H naught. Remember, the wording is very important. When we fail to reject, don't use the word except or anything like that, because remember, we're not proving anything here, okay? We can't prove anything. We're not sure of anything. There's always a chance that we might commit an error, which we'll talk about in a minute. Okay, for p-values. P-values, the only ones you'll have to calculate, because it's pretty easy, is using a z-table. Remember, you won't have to do it for a t-table. If you're doing t, that will be given in some form. But to actually calculate them, you only have to worry about z-table. What do? You look up the test statistic in your z-table and you subtract from 0.5. If you're doing a two-tailed test, remember you have to multiply that quantity by 2. Remember what the p-value does? It basically tells you the risk of being wrong should you reject your null hypothesis, which means the smaller the p-value, the more you reject, okay? So if you're given an alpha, if you just remember reject when the p-value is less than alpha, that helps a lot, knowing that alpha tends to range between 0.01 and 0.1. You should know that rule of thumb when you don't have an alpha, okay? Okay, so make sure you know the rule of thumb. So again, the little saying I gave you in the notes is when the p-value is low, H naught must go, and so that is why, so that helps you remember what to do with the p-values, okay? You should also be able to give a conclusion to your test in words. Remember, this is always stated in terms of whether there is sufficient or insufficient evidence of H1. So the conclusion has to be based on H1, okay? So there's lots of examples in your notes that you might want to go back in, or in the videos that you might want to go back and look at that will explain this to you, but it is important, okay? Probably the more difficult concept for the exam is to understand type 1 and type 2 errors. Remember, alpha is the probability of a type 1 error. Beta, which we really are not talking about, only in the context of helping you understand other things, beta is the probability of a type 2 error. But remember, the convention is you as a researcher choose what alpha is based on the severity of committing a type 1 versus a type 2 error. We can't control both, but remember these do have an inverse relationship. So again, as you increase alpha, beta will decrease, okay, and vice versa. So they do have this inverse but non-proportional relationship, okay? And then finally, we talked also about the power of the test, which is the probability of rejecting H naught when it's false. And we want to reject false hypotheses. So power is a really good thing, okay? So power is a good thing. It's exactly what we want to do. So we want powerful tests in this respect. So again, there's lots of trade-offs going on here. Remember the desire to have a small sample size because it costs a lot of time and money. The desire not to commit errors, but at the same time to have a high level, a very powerful test. So all these things are tugging at each other as we go through, as you go through.